Hi, as a data scientist, I often use machine learning algorithms to deal with time series. Seasonal time series is one of the most prominent examples of the signals observed in the industry. Such signals often have outliers, the drastic changes in the signal value that last for a short time. Such anomalies must be removed, otherwise would disrupt your models trained with mean squared error loss function. Due to its seasonality, typical value-related data processing techniques like trimming may not be applicable, especially if the difference between the minimum and the maximum within each cycle is comparable to or bigger than the mean of the cycle. Filtering seasonal time series may be tricky and often involves using complicated algorithms based on Fourier analysis of the frequencies. However, in this episode, I want to show you a simple algorithm based on the statistical properties of the values with a common distance to the origin of the respective cycle. In the comments, I've attached a link to Jupyter Notebook with implemented filter in a neat function. Feel free to test it yourself or use it in your project. Okay, so lecimy z tematem. In this example, I created a sine wave. For presentation clarity, I zoomed now on the first 9 seasons. In the next step, I noised the signal. Instead of typical Gaussian noise, I added a so-called spikes outliers to model sudden changes in the values commonly found in industrial applications. Such spikes can be, for example, a temporal increase in power drain in electrical grids or more intense water consumption in urban water systems. Once again, I zoomed to the first 9 seasons to increase presentation clarity. Now, let's signify the seasonality of the signal by dividing it into separable seasons. Then, we can sample the values having the same distance from the start of a cycle. In doing so, we create a distribution of first values in each season, second values in each season, and so on. When it's finished, we separate the seasonal signal into sub-signals of samples, each having the same distance from the start of its cycle. Then we can compute the distributions of each signal, and more importantly, get lower and upper percentile of the allowed region. Lower and upper percentiles are hyperparameters of the seasonal filter. They determine the range of observed values considered normal, and every sample outside this range to be an anomaly. In this example, I use the 5th and 95th percentile to determine ranges of normality. As a result, for every index of the sample in the cycle, there is a different filtering range. Let's look at the samples of the index 1 in the process depicted in the upper left corner. 5% of observed values are smaller than around minus 0.56 and 95% are smaller than about 0.12. It means that samples of index 1 in the respective cycle considered normal values between minus 0.56 and 0.12 and are not subjected to the filtering procedure. However, the values outside the range are considered anomalies and filtered out. There are different ways of handling such anomalies. The method I used was trimming the signal. If the value is outside of accepted ranges, it is brought to the closest value from accepted ranges. In this example, the value minus 0.7 will be changed to minus 0.56 and the value of 0.2 will be changed to 0.12. Keep in mind that each index have different filtering ranges. The ranges above apply only to the first samples in their seasons. The second values have ranges around 0.05 to 0.8 and so on. It is because we want to harness the seasonality of the signal for more precise filtering. Let's see the filtering results by observing the system components' responses one by one. Here you can see the original sine wave. Now you can see the original signal and the signal with added outliers. Now you see both noise signal and filtered signal, and all three together. Now I strengthen the filtering procedure by narrowing the accepted ranges. Right now the presented signal is filtered using the 5th and 95th percentile ranges. And here we have the same signal filtered using 10th and 90th percentile ranges. As you can see, the original signal is almost fully recovered from the noise. The presented algorithm did help me in a few of my projects. It can be further modified, mainly in dealing with abnormal samples. Of course, the substitution method presented in this episode has its drawbacks. One of the most important is the disruption of the signal probability density function, creating an accumulation of values probability on the edges of the distribution. It may affect the training of your models. However, it is still an improvement from the original state, and these drawbacks can be mitigated using more sophisticated approaches. Thank you for watching. Please consider leaving a like, maybe even subscribe, and have a nice day!